right. Okay, thank you very much, and I'd like to thank Aldo for beautifully... Can you hear me, or is there such a weird echo? I'd like to thank Aldo for introducing the topic so beautifully, and I'm going to follow up in the same spirit, but this time I want to give you the numbers, as Sandy put, that you can actually trust. So this is an attempt to go away from the toy model and more close to the observations and fitting them in the best way we can. But the topic is similar, and actually, given that we've never talked before and this has proceeded completely independently, I'm actually shocked to be put just after the talk that has attempted to do a very similar thing. So I'll give you my take on this. In particular, today I'd like to talk about the scatter around the star formation main sequence, and more generally the position of galaxies in the star formation rate stellar mass plane and how that relates to their star formation histories. So I'm going to go quickly through the introduction. Let me just introduce this plane. You already know about it, of course. Stellar mass, star formation rate, a passive sequence, and a star formation main sequence. And I'd like to draw your attention on the scatter, which is, I would say, rather substantial, even a redshift 0. And the topic of my talk today is going to be about the physical nature of the scatter. So in order to simplify this discussion and leave you with a couple of key ideas to keep in mind, let me just draw two parallel physical models for how to understand the scatter. So in the first model, galaxies fluctuate stochastically around the main sequence on fast timescales. You can see why this model is attractive because you can parameterize it via a toy model like this. You have, say, a small gas accretion event. Gas falls on a galaxy that's on the main sequence. The galaxy moves up, has high gas mass, high star formation rate for a little time. Then star formation rate drives outflows. Outflows kick out the gas. The galaxy plunges below the main sequence for a short time, and then you can imagine this happening over and over again over cosmic time. In this scenario, however, at fixed mass, a galaxy should have a fixed star formation history with fluctuations around it. You can imagine, on the other hand, the opposite scenario in which the position of galaxies in this plane are set, so to say, at birth, and they're correlated with other physical parameters that determine the position of galaxies from the beginning of time. So in a sense, this is also a fluctuation scenario, but the fluctuation is slow and covers the whole of cosmic time. So just to try and explain what I mean by that, let me again resort to a toy model. Let's start perhaps with something that's rather obvious. So again, let's pick a bin on galaxy mass around the mass of the Milky Way, and let's go to the passive sequence. You could imagine the star formation history of these galaxies looks something like this. They form most of the stars at high redshift, and then they quenched. On the other hand, I think everybody would agree that if I move at the same mass onto the main sequence, the star formation histories of these galaxies look more something like that. They form most of the stars later, and they form stars on a longer time scale, and that means they're still forming stars today. So I would say, well, it is natural to suppose that you could extend this scenario and think about putting boxes in the green valley, so somewhere between the main sequence and the passive sequence, and slightly above the main sequence, and that the star formation histories of these galaxies should look like this. Say a green valley galaxy would form most of its stars somewhere in between a main sequence and a passive galaxy. And a galaxy above the main sequence, on the other hand, has also had a systematically different star formation history. In order to test this scenario, I want to go to real data and perform archaeological full spectral fitting, which I think is not great, and you could give an hour-long talk on the systematics involved in doing this, but it's certainly a lot more, well, it's the closest we can get to getting this out of the data, I would argue. So what I'm going to do is try and select a data set which would have the best measurements of stellar mass, star formation rate, and integrated spectra at redshift 0. I want to study this plane at redshift 0 and cut it in little bins across mass and star formation rate. Obviously, such data set is MANGA, which was already introduced by our fearless PI, Kevin, yesterday, so I don't need to tell you anything about how we use integral field spectroscopy to map galaxies. I just want to point out that using manga to just derive the main sequence of redshift 0 poses a series of advantages with respect to using previous generation Sloan, in particular in mapping the H-alpha line to trace star formation rate. First of all, we don't suffer from aperture effects, and then secondly, we can correct a lot better for a lot of other residual systematics like the presence of AGN, liners, or low ionization nuclear emission line regions, diffused ionized gas, etc., etc. And if you want to read all the gory detail, you can go into some of my papers from the last couple of years. I could give you just the punchline. The punchline is if you look at galaxies that are star forming everywhere, we recover the same star formation main sequences for old Sloan data. But if you go into the Green Valley, old Sloan is hopeless because most of these galaxies have quiescent bulges, and so the central fiber doesn't actually give you a good measurement for star formation rate for the whole galaxy. And of course, Sloan has had several iterations trying to correct for that, but really the correct way of doing this is to look in the manga data. So having said that, let me move towards full spectral fitting. This is a now established techniques that keeps having several systematic uncertainties. I do not want to give you a list of systematics. I just want to give you a feeling for how this is done with the real data. So as an example, these are two galaxies around the same stellar mass, say 10 to the 10. This is a star-forming galaxy, main sequence. This is a passive galaxy. These are their integrated spectra within one effective radius derived from the manga data, signal to noise of around 100 in both cases. Here I've subtracted the emission lines, of course, and then black is the data and red is best fit stellar population model. And as you can see, I would say we get extremely good fits, and we can get some information on the stellar populations that make up these two galaxies. So just as an example of what we can get out of this data, this is the plot I want to present most of my results later on. So I'm just going to walk you through the axis. So this is a general observational way of plotting star formation histories because it basically hides some of the systematics that are difficult to quantify. So on the x-axis, I plot look-back time. 0 is today, 14 gigayears is the Big Bang. And on the y-axis is a cumulative mass growth history. So basically the amount of stellar mass that was produced by a certain time divided by the total amount of stellar mass today. So obviously today you formed 100% of stellar mass in both galaxies. But say if you look at 60%, you can see that my main sequence galaxy formed 60% of its stellar mass later than my passive galaxy. And to answer Sandy's question, it's really difficult to believe these numbers, say 3 and 6, but the relative hierarchy of these two numbers is pretty robust. So the passive galaxy has formed more of its stars earlier on, even though I cannot tell you whether this is 6 gigayears, 7 gigayears, or a slightly different number. And this is related to the systematics with stellar population modeling, etc. So this was two galaxies. Let me generalize to the whole sample. Obviously, we cover galaxies from 10 to the 9 to 10 to the 11. And here I'm plotting main sequence galaxies in a solid line and passive galaxies with this dashed line. Same plot. You see the same thing. This is now stacks, so all galaxies of this particular stellar mass. And this is main sequence galaxies within the scatter of the main sequence. And you can see, of course, the passive galaxies have formed earlier than main sequence galaxies, which is no surprise and what everybody was expecting. So the next thing I want to do is populate this diagram with galaxies that are below the main sequence, so you'd say in the Green Valley, and galaxies that are above the main sequence today. So I'm always talking about relative position with respect to the main sequence today. And this is what happens. So blue is above the main sequence and red is below. And I think I've studied this for a long time. I've tried different stellar population models, different model assumptions, and I think it's actually very significant. There's a strong correlation between the star formation history of a galaxy and its position with respect to the main sequence today, exactly in the way that I hypothesized earlier, in the sense that Green Valley galaxies have a star formation history that's between, say, main sequence and passive, and vice versa, galaxies above the main sequence have formed even later. I'll take your question at the end. Okay, so in my last couple of slides, I want to highlight a couple of consequences of these different star formation histories, which perhaps go in a comparatively different direction from what the previous speakers has highlighted. One of them is a logical question that goes back to a comment Joel made in the discussion yesterday, which is chemistry. Chemistry is a powerful tracer of star formation history. Is there any chemical differences between galaxies that have different star formation histories? And of course, there has to be. So let me build your intuition for what that should look like. Again, I'm going to use a toy model. So this, in the spirit of the previous talk, this is a toy model star formation history. It's a delayed tau model for a passive galaxy and a main sequence galaxy. I'm then going to take these star formation histories and put them in a chemical evolution model. In this case, this is a simple bathtub chemical evolution model with a couple of free parameters. So we'll capture things like recycling, there's a yield, there's an alpha loading factor, there's a efficiency of star formation. And I can crank the wheel and get you the answer for how the metallicity will change as a function of time. Now I'm going to focus on stellar metallicity as opposed to the gas metallicity, and that's for a simple reason that we cannot measure gas metallicity in passive galaxies. There's to date no way of doing that with optical spectra. So let's look at stellar metallicity. And this is what happens. So inevitably, the passive galaxy has higher stellar metallicity today than the main sequence galaxy. And if you want to think about this, it's because your passive galaxy builds up very quickly, and so it enriches very quickly, and so it forms a lot of high metallicity stars already at high redshift, while your main sequence galaxy builds up more slowly, and so it forms a lot of lower metallicity stars at high redshift, which you then cannot get rid of, and so stay there, and you see this interstellar metallicity difference. So this is from a toy model. Let me see, is this burnt out in the real data? Do passive galaxies at fixed mass have higher stellar metallicity than main sequence galaxies? Of course they do. This was pointed out beautifully in a paper by Yinji Peng using data from the Sloan survey. And without further ado, you can now predict what would happen if I put a Green Valley galaxy in there. It should sit in the middle. And if I put a galaxy above the main sequence, it will have even lower metallicity, right? So that's exactly what happens if I do that with my manga data. This is a busy plot, but basically what I want you to read is that blue is above the main sequence, has lower stellar metallicity. Say red is below the main sequence in the Green Valley, has higher stellar metallicity than the main sequence. And interestingly, these trends are also found in large cosmological simulations. It was pointed out by people in EAGLE. I took the Illustrious catalog and did the same plot, and while the magnitude of the effect may be different, it's also obvious in this simulation. So it's something that is already there in the models that people have built. There's also a link to the fundamental metallicity relation for gas phase metallicity, but I do not want to go into that for lack of time. So in my last slide, I want to point it out that, as the previous speaker has perhaps argued, there is a relation between the star formation history of galaxy and their halo assembly history. This is perhaps obvious. And this was pointed out in a very beautiful paper by Mathieu and Shea using the EAGLE simulation. They did basically the same thing as I did, only of course they couldn't be bothered to do it with the real universe, and they just used their simulation. But this is very beautiful. So these are, again, our cumulative mass growth histories. The time is plotted upside down, forgive me, the theorists. It's also not normalized to 1, but basically you should see a rainbow here, and you do see a rainbow. And what happens, of course, is in the simulation you have halo, and so you can track how the halo mass grows. And what they argue is that, to some extent, the halo mass growth follows the assembly of the stellar mass. So this has interesting consequences when you want to do abundance matching in terms of linking the stellar mass with the halo mass, and linking the star formation rate with the halo assembly history or timescale. And there's been a lot of work done in that direction already. So this is further confirmation that's a useful way to think about it. So let me leave you with my conclusions. I think they can be summarized with this cartoon picture. If a galaxy is above the main sequence, has more extended star formation history, lower stellar metallicity, the halo grows later. Vice versa, if a galaxy is below the main sequence, it's in the green valley, has an early and compressed star formation history, higher stellar metallicity, and their halo assembled earlier. That's it. Thanks.
Well, one thing that always surprises me is that people show this kind of sequence of passive galaxies, right? And there is no sequence, I think.
There is no sequence.
So so that's a bit misleading, right? But well, of course, we know where it comes from. It comes from the color magnitude diagram. But I think it's important to keep in mind that it's not obvious that there is a sequence at all if you look in the star formation plot. Now, what I think is interesting is that you seem to show that also galaxies that essentially are above or below the main sequence also show this trend, so similar to essentially passive galaxies. And again, this raises the question: is there really a bimodality, or is it just one sequence, right, from the most star-forming one to the most passive one?
I can only say that I agree, and I think that's an interesting question to ask. And I totally agree. There is no passive sequence. The fact that it's plotted there is, yeah, we've had this discussion, and I don't want to go against that. It totally fits within the spectrum.
One of the things that perhaps indicates that galaxies above the main sequence and below the main sequence tend to stay where they are is their correlation functions. Alison Coyle and collaborators pointed out that the correlation functions above the main sequence, the galaxies are less correlated, and below the main sequence more correlated. And of course, if you go far below the main sequence to the passive galaxies, it's well known that red galaxies have a much higher two-point correlation function.
Right.
Have you looked into issues like that as you're looking at these manga galaxies, or are you focusing more on the individual galaxies?
I think that's the logical way forward. It's of course not clear how to interpret the signal, so you'd want to model it within a galaxy halo connection type of model, and I think that would be very exciting, and it would motivate a further look at the redshift 0 data for sure. I would think so. Sure, but that's a very, very small population, redshift 0, right? Well, a higher redshift, there should be a larger population, right? I didn't say that. Well, but I didn't show any data to, yeah, I didn't discuss that point.
Okay, I'm sorry, but we have to move on. Our next speaker